going to do is we're going to go over the homework that I assigned yesterday, and then we're going to do a little bit of notes, and then I'm going to give you an assignment that is a lab that you can work on the rest of today, and then you'll be given most of the day on Thursday to work on as well. So yesterday we talked about the current worksheet, and all right, here we go. So electric current, a negatively charged object has more or fewer electrons than an object that is neutral. You guys can answer. More, right? Okay, if you have more negative charges on you, you're going to be negative. Okay, a neutral object has exactly the same number of electrons as protons. Electrons flow from areas of higher or lower voltage to areas of higher or lower voltage.
Higher to lower.
Yep, you go from high to low. Again, you can kind of think about voltage like it's a hill. You go from the top of the hill down to the bottom of the hill. Number 3, voltage difference is measured in amps or volts. Yeah, don't overthink that one. All right, number 4. The current in a circuit is measured in volts or amps. Amps. We just said volts measure voltage, so the other one must be true, right? Okay, current is almost always the flow of electrons or protons. Electrons, right? Why don't protons move? Okay, protons are in the nucleus of an atom. And an atom, if the nuclei could move, we wouldn't have solid objects, right? So everything that you would touch would just kind of be like milky wax, and it would move around. So the protons are the things that give the physical structure. Protons are 2,000 times more massive than an electron. Electrons are the things that are free to roam around. And so they're the things. The one exception you would see to this would be in a like if you had salt water. If you had a saltwater solution, then you don't have a solid object, and you have positive, what we call ions, which we'll be talking about after break, and negative ions. And then the positive charges can move around because it's in a liquid. It's not holding its shape there. All right. When a dry cell / battery is connected in a circuit, the flow of electrons move from the positive or negative terminal to the positive or negative terminal. Negative to positive, right? An electron's not going to try to go to something else that's negative because it doesn't like other negatives. It's going to get repelled around to the positive. The voltage difference between the 2 holes in your wall sockets that you plug things into. We didn't talk about this yesterday. So is it 12 volts or is it 120 volts? Anybody know that one?
120.
It's 120, right? And then sometimes in your house, like if you have an electric dryer or if you have a stove and you've ever seen where those plug in, they've got these huge like plug-in things. Those are 220 volts. So it takes like twice as much energy to make those things work. Yeah. Like you can't, like all the regular standard plugins we have, those are all 120. The ones for a washer, or dryer, or stove, the plug is shaped differently and the prongs are different, and they don't work. So like you couldn't plug your phone into a 220 thing. Just wouldn't work. Yeah. You probably could. I don't know why you'd want that. I don't think that's gonna, like, you're thinking, could I charge my phone faster? I don't believe that would work. I also am not sure that would be safe. I know that, like, for example, people who have electric cars, like you can have a charging pad in your house, like in your garage. So like you can just drive your car over it, and then that pad is plugged into the wall. And so like Mr. Kirsten, he's a chemistry teacher here. He has a Nissan Leaf. And so he had a 120 volt outlet in his garage, but he got it converted to 220. The 120 will work, but yeah, it will take longer to charge the car that way. But yeah, I'm not sure what if you convert down from 220 to 120, I'm sure they probably have some kind of adapter, and I'm sure they've made it safe. So, but still, you still wouldn't be getting 220 into your phone. All right, resistance is measured in ohms or volts.
Ohms.
All right, copper has a higher or lower resistance to electron flow than tungsten. Lower, right? Why did they pick tungsten as the other metal here? I mean, tungsten is not something that we're all super familiar with, but in old light bulbs, not fluorescent light bulbs, but in the regular ones like incandescent bulbs that you still might have a few of around your house, the little filament in the light bulb is tungsten, probably, okay? And so you're running electric current through that little filament in the light bulb, and because of its high resistance, it gets hot. And when it gets hot, it glows, and we have light. Okay, so again, that's different from the fluorescent lights we have here. That's a gas that's getting electrified. But in the old incandescent lamps, you've got a filament that's getting hot and glowing because of its higher resistance. All right, number 10, according to, oh, and by the way, as long as we're on that, you can actually use a pencil lead as a filament in a light bulb. So if I'll show you that another day. Okay, anyway, where are we here? According to Ohm's law, I, current, equals voltage divided by resistance, or voltage equals current divided by resistance. Yeah, you guys, you might not know that. If you looked ahead in the notes, you would see it's the first one. Okay, I equals V over R. We'll talk about that today. The symbol for ohms is omega, or the degree symbol. Omega, right? In the equation, I equals V over R, oh look, they kind of gave it away. I is expressed in ohms or amps. Amps. I is current, and current is measured in amps. In the equation I equals V over R, V is expressed in volts. All right, number 14, a wire with a resistance of 3 ohms has a greater or lesser resistance to electron flow than a wire with a resistance of 5. Lesser, right? Yeah, don't overthink that one. That one hopefully is pretty straightforward. And then number 15, if 2 copper wires are the same length but different thicknesses, the thinner or thicker wire has a greater resistance. Thinner, yeah, the thinner a wire is, the more resistance it has, because it doesn't have as much surface area on the outside of the wire for the electrons to flow. So, you know, they're bumping into each other more often. If I have a thicker wire and they travel on the outside of it, there's just more real estate. Okay, so go ahead and take your notebooks out. Let's move on to just a few slides here regarding Ohm's law and circuits. Okay, so in the worksheet, you saw something related to what we call Ohm's law. All right, and Ohm's law, Ohm is the last name of a guy who did a lot of work with electricity, obviously. But what he found out was that your voltage, your current, and your resistance are all related to each other via this equation. Okay? So what does that equation really mean? Well, I'll let you write this down first, and then I'll talk about it. that's kind of what we finished with yesterday, talking about what the different units are for each particular quantity. Again, voltage is kind of it's kind of like a force that's pushing the electrons through the circuit. That's technically not true, but you can kind of think of it that way. Current is the flow of the electrons, and the resistance is sort of the electrical friction. It's keeping electrons, trying to keep electrons from moving. All right, so what we see in this equation is that current and resistance are what we say inversely proportional, meaning that if you increase current, it must be because resistance went down. Yeah, pencil. All right. So that's what inversely proportional means. It means that if you increase one thing, the other thing does the opposite. So if I double my resistance, my current gets cut in half. If I triple my resistance, my current gets cut down to a third. If I triple my current, that must mean I cut my resistance down to a third of what it was, right? And hopefully that makes logical sense. If there's less resistance to electrons flowing, then more electrons can flow, right? For any given voltage. Now, if I leave, this question says, if I leave the resistance the same and I increase the voltage, what's going to happen to the current? Well, it's going to go up, right? If I push harder, I can get more things to go through. So your current, and again, this is the way it was written on your worksheet, you can kind of think of it this way. If your voltage gets bigger, I gets bigger. If R gets bigger, then I gets smaller. If I divide by a big number, I get a small number back, right? And that's called, again, Ohm's law. All right, I just got to find a plug that works here. Okay, so the last thing I want to talk about are electric circuits. And again, we are trying to get electrons to do what we want them to do and go where we want them to go and go through the devices that we use, light bulbs, phones, TVs, toasters, whatever you can think of that you plug in, hair dryers, microwaves, refrigerators. In order for that to happen, though, you need a circuit, which means you have a pathway that goes from your power source, either the plug in the wall or the battery, through your device, and then back to the battery or back to the wall. That's why there are two prongs on that plug that you plug in. One is for in, one is for out. And actually, like I said, that shifts back and forth 60 times a second for alternating current. But for a direct current device, like anything that uses a battery, you have electrons leaving the negative going through the device and coming back to the positive. And they have to. If I unhook this from this one terminal on the battery, it's not like there's a current flowing and then it just dead ends. It's just there is no current. If it's not a complete pathway all the way around, if it's not a complete circle, there is no movement of electrons. All right, so everything you plug into your house, every place you plug something in, that's a circular pathway to your device, back to the power plant, and from the power plant back to your device. Okay, it's everything is a big loop. And there are two main types of circuits that we're going to talk about. We're not going to talk about how you need to know everything about them. All right, I'm going to go back here. This is the last slide. You have two main types. You have a series circuit, which is just a simple circle, station to station to station. So like you start here, goes through one light bulb, goes through another one, and then comes back. One pathway. There are no choices for the electrons. They have to go through every single thing that's in it. The other possibility is the parallel circuit. And that's where the electrons can choose to go through one and then back, or they can choose to go through the other one and then back. And if you unscrew one light bulb, the other one still works. In the series one, if you unscrew one light bulb, nothing works because it's not a circuit anymore. And for these parallel ones, or even series, but parallel, I could have another set and another one and another one, another one. I can keep going further and further and further. For the series one, I have to, every one I put in has to be another like link in the chain. It has to be from one to the next to the next to the next. In reality, a lot of the things we have are complex circuits which put these two things together, but we're not going to get there. If you take physics someday, we do a lot of work with that. All right, so any questions so far? Okay, so then let's talk about the circuit lab. And I want to show you kind of how this all works. And this is going to be due on Thursday. So you open up the document that you've been given. And then you click on this link right here. You click on that link, and that opens up the lab simulator. And really, you can use the intro or the lab. It doesn't really matter, I don't think. But you click on that. All right, for now, just pay attention. Don't do anything on your computers. Okay. All right, so to use the simulation, the things that you're going to use are batteries, wires, bulbs, switches, maybe a fuse. I don't know. Really, I don't care if you use a fuse. It's these other ones that are important. And so what it's going to ask you to do is it's going to ask you to put together these things in such a way, right, Jackson?
Yeah. That
allows us to make something light up. So here's my battery of no particular brand. Okay, and then I'm going to rotate this up here, and I want to make a light bulb light up. So I bring this down. And I can just connect that there, and now it works. And you can see the electrons moving. You can see how bright it is. what if I, oops, if I click that, I can break that connection. Let's put another battery in. Even brighter now, let's put another one in. Super bright, and again, you can kind of see how that goes. Then you can put in things like resistors. So I want to restrict the amount of current that can flow. And so it's not as bright now because this is put in specifically to lower your current. Your house, like I said, operates on different circuits that are up to 15 amps. And the reason you don't want it to go over that is wires can get hot and that can start fires. And so every so often you hear about people who have an electrical fire at their house. These resistors are put in purposely to, let's bring it down a notch. And then if it goes over, if something fails there, you have a circuit breaker in your house that'll just turn the circuit off. And it'll be like, nope, too much current, you can't do that. So anyway, if I want to put a switch in, I can go like this. I'll put a switch in here. All right, and now it doesn't work, right? Unless I close it. Now it works. Then I open it. Off, on, off, on, off, on. Okay. So that is the flow of current. Now, what else do I want to mention here? So really today, we only have 15 minutes left. Try to work through, begin part 1 and just kind of see how far you can get. And then when you're done today, you don't have to work on this at home. You can just be done. And then on Thursday, when you come back, we'll work on the rest of it. Okay, so no homework today. And partially that's because, I mean, look, I'm not going to, you know, if you go home and you do homework, like you're being a rebel and doing homework on your own, that's fine. But I would prefer to be able to help you if you have questions. But if you think it's cool and you want to play with it and go ahead, you know, go ahead. But I am not assigning it today. You should be able to, we'll have all day on Thursday to work on this and get it done. Okay, so any questions? Just a reminder that I have to have grades in by Thursday. So if you had anything you were going to make up or turn in that hasn't been turned in yet, now would be the great time to do that. Otherwise, distance learners, you got anything? Okay, well, you guys can go then.